Hey guys, good morning. I'm not here today. My son is super sick, but I still needed to get this lesson in. And the last time I did a video, it didn't work so well, so I'm gonna try to do it this way. You should have a white note and a green note. The green note is your homework. That's gonna be a new video tonight. So make sure that you get that done. I'll go over any questions tomorrow, but please, please, please feel free to email me if you have any questions. This lesson today, our first one, which is 5-1, is going to be on the white sheet of paper. Your green one will be tonight. So 5-1, our essential question today, we're starting a new topic, which is system of equations. Our essential question today is, how do I solve systems by graphing? How do I solve systems by graphing? So what is a system of equations? You've actually already started working with systems of equations. Systems of equations is basically two equations that can be solved, or that have either one, many, or no solution, in which case they intersect, or that they can both be equal to the same thing. So the easiest definition for what is a system of equations is two or more equations that can be graphed on the same plane. Two or more equations that can be graphed on the same plane. And remember, when we talk about plane, we're not talking about a flying plane, but it's like that coordinate grid or a coordinate plane. So how do I identify the points in which satisfy a system of equation? What that means is, in order for a system of equation to be satisfied, they cross at some point. And so you've been working with parallel lines and perpendicular lines. Now, perpendicular lines are actually a system because they cross at one spot. You could also have two equations that meet at the same spot, so they're gonna have infinite amount of solutions, or you can have two lines that never meet, which are called what? And these have zero solution. So how do I identify points that which satisfy a system of equation? It's where both equations have the same coordinate pair that matches. The same, and I'm just gonna write ordered pair that solve both equations. Sorry, that got really smashed up there. But satisfying a systems of equation is basically that ordered pair in which they meet, or the ordered pair that I can plug into both equations and both are gonna have satisfactory answers. So in order to do this quickly and easily, we can circle the points which satisfy a system of equations by plugging these in. Remember that this is always my x and this is always my y. So all I have to do is plug my x in, and does it equal my y? Plug my x in, does it equal y? And it has to do it for both equations. So this first one is 0, so that makes it pretty easy. Does 4 times 0 minus 1 equal the same thing as -0 plus 4? No, they don't. How about this one? If I plug in a 2, does 4 times 2 minus 1 equal 7? Yes. Does it work for the second equation? Does -2 plus 4 equal 7? No. So here we go again. Does 4 times 1 minus 1 equal 3? Yes. Does -1 plus 4 equal 3? Yes. That's our answer. I'd like for you to do number 2 by yourself. So maybe our guest teacher could press pause. All right. Check your answer with a neighbor. Okay, so there are three types of systems. What are they? Just like single equations and inequalities, systems can have one, many, and we sometimes write that as saying that they have infinite, and that's when you actually are graphing the same line. They are infinitely touching, or no solutions. We often also call these three types of systems independent, because they will have one solution. Dependent, which means that they depend on one another, so they have infinite amounts of solutions. Or inconsistent. So consistent systems have a solution, inconsistent do not have a solution. So these are some examples, and I'm just gonna briefly sketch out what these look like. You can go back in if you'd like and actually plot them out, but I wanna kind of show you what these look like. An independent solution that has one solution, and I can draw this one, where 2 times x, so that means that I'm going up 2 over 1, up 2 over 1, up 2 over 1. So my line kind of goes like this. This is my first line. And then my second line is just an up 1 over 1, but I'm starting at 1. So I'm going like this. And this line right there. And I'm noting that this point right there, that's my solution. There's one place where this line is crossing. Infinite solutions is, like I said, where if I were to graph these two, this one right here happens to be at -3 with a slope of 2. And if I quickly go through and do this again, I can assure you it's actually the exact same line. So we end up with infinite solutions. It is infinitely touching each other. No solutions, and like I said, you can go back through and solve these two equations and graph them, but this is where you're gonna end up having 2 parallel lines. There's no solutions. These have no intersections. So we have one intersection, infinite intersections, no intersections. So here again, we have independent with one, independent with multiple, inconsistent with no crossing. Okay. When given a graphing calculator or graphing paper, the easiest way to solve systems of equations is to just graph them. And I'll talk to you tomorrow about how to use your big calculators. It's just easier if I can show you when I'm kind of around you. But you know how to graph equations onto a graph. So what we're gonna do is we're gonna start here and we're gonna graph these ones here. I'm gonna notice my slope and I'm gonna notice my y-intersect. And what I like to tend to do is I tend to pick one color to do both equations. So then that way I can really kind of see what's happening. So on my first equation, I'm gonna start at 1, and my slope is up 3 over 4. So I'm gonna go up 3, 1, 2, 3 over 4, 1, 2, 3, 4. Up 3, 1, 2, 3 over 4, and then I am going to make a line. It's really helpful if you can make straight lines on this, but it's not a terrible, if you can't, you should still be able to kind of see your own writing. On this one, I'm gonna start at -4, 1, 2, 3, 4. And my slope this time is down 1 over 2. So I'm gonna go down 1 over 2, down 1 over 2. Now, I'm noticing that my line is gonna cross somewhere over here, so I'm gonna go backwards with this line so I can make a really nice, precise, where is this crossing this line. So I'm gonna go back to up 1, back to up 1, and I'm noticing it's that point right there that this line is gonna cross. So that intersection, I need to give somebody directions on how to get to that intersection. So if I start at my origin, and to get over to this intersection, I'm gonna go back 1, 2, 3, 4. So I have a -4 for my x, and I'm gonna go down 2. My y is down 2. The solution is just the same thing, where you're just rewriting that ordered pair. Now to verify algebraically, what that means is that I'm gonna put this in to both equations and make sure that it satisfies both equations. So for my first one, we're gonna put this -4 in. So I get y equals 3/4 x plus 1. I'm gonna put -4 in. Does -2 equal 3/4 of -4 plus 1? Well, 3/4 of -4 is -3 plus 1. Does that equal -2? So we know that this solution satisfies this equation. Now let's try it for our second one. So now I have y equals -1/2 x minus 4. I'm gonna go ahead and put my solutions in. Does -2 equal -1/2 of -4 minus 4? 1/2 of 4 is 2. Negative times a negative is positive. So does -2 equal 2 minus 4? Yes. Because they both are satisfied with this solution, we know that this is a solution to the system of equations. We're going to do one more together. So I am going to choose a green line for this first one. So I'm going to go ahead and put my y-intercept, 1, 2, 3, 4. And then my slope is down 3 over 4. 1, 2, 3. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. Give yourself as best of a line as you can. Ooh, that was a really crummy one. Now I'm going to do blue for this one. So I'm going to start at -3. 1, 2, 3. And this one is up 1 over 1. But I can see immediately where that is going to cross. So it's crossing right there. So my intersection is at 1, 2, 3, 4, positive 1. So my solution is 4, 1. Verify it algebraically. Y equals -3/4 of 4 plus 4. 3/4 of 4 is 3, but it's negative. So does 1 equal -3 plus 4? Yes. Okay, now let's do our other line, which is the y equals x minus 3. So we get 1 equals 4 minus 3. 1 equals 1. It is verified. This one, the only thing that changes is what do we have to do to this second equation? It is not in slope-intercept form, so we need to go ahead and change it into y equals mx plus b by subtracting x to both sides. So we end up with y equals negative x minus 2. So now I have -2. I'm going down 1 over 1, down 1 over 1, down 1 over 1. Right here, I have +2, and I'm going up 1 over 3, up 1 over 3. Here's another example where my crossing is actually going to be, I didn't extend my line quite far enough. So I'm gonna come back and do my, do my slope on the blue line a little bit further. Down 1, back 3, down 1, back 3, and then you should be able to see where that intersection is happening. So this time our intersection is at -3, +1, 3, +1. I'd like for you to go ahead and stop, verify that this answer is correct. Maybe the guest teacher can pause it, and we can move forward. So what I'd like for you to do is go ahead and reflect. What did you already know about systems? Was it easy? As far as graphing goes, it's the easiest way to solve. So if you have a graphing calculator available, it's always easy. Otherwise, if you have graphing paper, it's super easy. Generally speaking, I'm not going to ask you to graph some super crazy equation. We'll talk about how to solve those with substitution in your video tonight, and elimination, in which case we'll do that tomorrow. Again, if you have any questions, please email me. Also summarize, how do you solve by graphing? Easiest way that I can think of, make sure your equations are in slope-intercept form, graph using your slope and your y-intercept, find the location where they meet. Have a good day, guys.